Yes, Naveen, let's start.
Okay, so is it streaming?
Yeah.
Uh, Okay. Good evening, guys. Welcome all. So today we are going to discuss the solutions for this row ICRB question paper. I'll be dealing the solutions for manufacturing and industrial engineering part, and here we are discussing the solutions for the questions in set E. Okay. So the first question that they have given is on welding. It's a little calculation intensive, not very calculation intensive. For the sake of examination, it is intensive, but it is very simple question that has been asked in GATE also previously, and here also the same kind of question has been asked, which we have solved in our classes. Very so many number of times we have solved this thing. Same question is repeatedly asked, so it's straightforwardly we can go and do the solution. So let's read the question here. A weld with triangular cross section as shown below. Okay, let me take this. As shown below is to be produced on a steel workpiece by shielded arc metal welding SMAW using steel electrode. Okay, if a 24-volt power supply is used, okay, let us write what is given. Okay, so let's write what is given. What is given? The power supply is given and 24 volt. So voltage is given. So voltage is equal to 24V, right? And the welding speed is 12 mm per second. So welding speed, I will write as new is 12 mm per second. Okay. So please remember this is welding speed, right? And what is current needed? So what they're asking, the current is what they're asking, right? Assume the efficiency of as 80% and the specific energy to melt is, so let's there also is given specific energy, right? So specific energy, generally specific energy is denoted by U, capital U, is equal to how much? 8 joule per cube. Good. Now, so 80% efficiency. So what is the efficiency they have given? The heat transfer efficiency is 80% because you are providing some power, right? And that power has to convert into heat and it has to melt the material and get deposited into this cross section here. That is a triangular cross section. Okay. So this is what we have to. Now let's do one thing. Let's take this triangular cross section and denote it with some points. Let's say this is A, B, and C, and that is what is the weld deposition that is happening. Right now, we have to fill that. Right? So now these are the conditions that they have given, and they're asking us to find out what is the current required here. Okay, so let's start with the basics. That is, first we are trying to generate. We want to generate heat. We want to input heat to melt the electrode, right? And where the heat is coming from? The heat is coming from the power source, right? So let's write heat input heat input to workpiece, right, is equal to power 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 into efficiency of heat transfer. Okay, efficiency. So this eta H is efficiency of heat transfer. Heat input or heat transfer. Right? Now, so please remember that this heat input we will denote it as HI. And also the unit of this is not joules, joule per second. Please remember that. That's very important. Don't make mistake with the units. Okay. Because this power V into I into efficiency. Right. So this power is joules per energy per time, joules per second. So this is also joule per second. This is very important. Okay. Now, what is power P? So I'll write HI is equal to P into H. What is power? Power is V into I. So HI is equal to voltage into current into heat transfer efficiency. This is good, very good, right? And remember, this is joules per second. Why I'm telling joules per second, I'll tell you. Okay. Now, what is that? They have given the specific energy to melt the material. So now this is the heat that is what we are providing from our side, right? And what is the heat that is required to melt the material is Hm. Okay. So let's say Hm is heat required. Okay, Hm is heat required, or Hm is heat required for melting, right? Heat required. Okay, let me write this as full statement, then you understand. Heat required for melting is equal to heat required to melt a unit volume of material into volume of material melted per unit time. This is very important, right? So, and I'm denoting this as HM, right? So HM is equal to the heat required to melt unit per is a specific, the specific energy or specific heat into the not specific. Okay, let us not write that. Okay, here I'm going to do something. Okay, so the thing is, okay, this is U only, sorry. Now, volume of material melted per unit time. Okay, what is the volume of material? First, we have to calculate the area of this thing, ACB, and the length. The length will be some length L, right? And that length L here they did not give. They gave with respect to the welding speed, right? The welding speed is 12 mm per second, right? So what we are going to do, volume per time is area into length by time. So I can write that as area into velocity, right? I can write into area of weld into velocity, welding velocity V. But we don't know area of weld because we have to calculate this. So that will come from the geometry. So let's take this triangle, and what is this height? So the perpendicular distance from A to CB is 5 m and this angle is 45 degrees. So let's take the diagram. This is A B, and C. Let's take a perpendicular from A to CB, that is D. And we know that AD is 5. This is 5. And obviously, as this is 45, I can take this also has 45. Right? So this is 45 degrees and this also is 45 degrees. Okay. Now my aim is to find out the area. So I can take two triangles, right? Triangle ADB and triangle ADC. Both the triangles are symmetric, right? So AW, or area of weld, is equal to half area of triangle, half CB into AD. So I don't know CD, or I don't know CB. So I can take triangle AD into DB, right? Plus half AD into CD. And please remember, CD will be equal to CB because angles are same, right? So I want to find out I know AD here, I know AD. What is AD? From the diagram, AD is equal to 5, 5 mm. I want to find out the value of dB. So what I can do, I can write tan 45 is equal to, what is that? I can write as dB by AD, right? Tan 45 is 1, dB by AD is 5, so dB is equal to 5 mm. dB is 5, I can write CD also same because both are symmetric. So here I can write, as dB and CD are same, I can write 2 into half AD into dB, or CD, anything is fine. So 2 into, okay, let me cancel out this. A simple question, but I'm doing it a very elaborative way. But yeah, AD is 5 and dB also is 5. So this will be 25 mm square. Now let's go to this. So we got the area, we got the velocity, we got specific thing, we got voltage, we got heat transfer, we got I. So heat input should be equal to heat required for melting. If there is some melting efficiency given, then you have to consider melting efficiency. Since they do not give any melting efficiency, I can write as heat input is equal to heat required for melting. What is heat input? VI, heat transfer efficiency. VI, heat transfer efficiency, and HM is UAW into velocity. UAW into welding velocity. That's it. Substitute all the values. Right. What is V here? V is given 24. Current we have to find out. What is the efficiency of heat transfer? 80%. So I'll write 0.8. And specific energy is 8 joule per, and please remember this also is joule per second, right? Because you just calculate the units, you'll get joule per second. Okay, so we are equating same units, do not equate different units once. Okay, 0.8 into area is 25 into welding speed is 12. Just do the calculations and we'll get I is equal to 125 ampere. Yes, I've done it in a very lengthier way. You can do it in a very small amount of time, but here the purpose is to explain some concepts. I've done it in a very lengthier way. You can do it within below 1 minute. You can do it if you have the concept. Okay, so the answer is C. Next, this question is from the machining. And the question is, the 20 diameter aluminum rod is turned to 19 diameter in a single pass. It means that let me write what is given. Given initial diameter di is equal to 20 and final diameter df is equal to 19 in a single pass if axial speed of tool is 200 per minute. So what is there? Axial speed is given, right? So axial speed, let me write. Actually, axial speed is nothing but feed only. This feed is 200 per minute. The feed in actually what they've given is feed in feed per minute. Generally, feed in a turning operation, feed will be in per revolution, but here they've given as per minute. The spindle rotates at 600 rpm, so n is given 600 rpm, and the metal removal rate is nearly. So they're asking what is MRR, right? So now what we have to do, we have to ask us what is MRR. MRR is nothing but MRR is material removal rate is volume of material removed divided by time per time, right? So in machining or especially in turning operation, what is the volume that is being removed? Chip thickness, uncut chip thickness into width of chip into length of chip. So thickness, width into length. So all are uncut. That is the material is being removed divided by time, right? So we can take this length by time as cutting velocity, right? TB into PC. And in our class, we have even discussed that we can say uncut chip thickness as feed F and width of uncut chip can be written as depth of cut, DOC, depth of cut, D. So I can write here from here, MRR is equal to F into depth of cut D into cutting velocity VC. Right? So what is given here, we have to see. So nowhere near feed, but this feed, remember, this feed what we are getting, this feed is, it should be in per revolution, but in question they have given in per minute. Okay, that is very important, you have to understand that. Okay, so first for this we have to find out the speed in per minute, per revolution, depth of cut we have to find out. I'll tell you how to find out, and we have to find out the cutting velocity. If you can find out these three, MRRS done. Okay, so first we will go for the feed in per revolution. So feed in per minute can be written as feed in per revolution into n, that is revolutions per minute. See, if you calculate this revolutions, you'll get per minute. So what is given? This is given. So what is that value? The value is 200, right? So 200, we have to find out feed in per revolution. F into n is given. What is the value of n? 600. That's it. 600. So F is equal to 200 by 600. That will be equal to 1 by 3. Let it be 1 by 3. Don't convert it to decimals. Okay. Now we found the value of. So this is the formula that we have to apply, right? So F is found out in mm per revolution. So this is mm per revolution. And depth of cut should be found out. So what is depth of cut? Diameter is reducing, right? So initial diameter, final diameter. Right? So the diameter is being reduced. So this is 20. Is it 20? Let's check. Yes, and this is 90. So what is the depth of cut? Depth of cut is this. So that is depth of cut is equal to d d initial minus d final by 2. Minus d final by 2. So what is d initial? 20 minus 19 by 2. So depth of cut is equal to 1 by 2 is equal to 0.5. Okay. And next is cutting velocity. Cutting velocity Vc is equal to rotational speed pi d n. That's it. So we cutting velocity is pi into what is d? Diameter is given. Okay, now the question is, as we proceed, the cutting velocity will be reducing. So which velocity you have to take? You have to take initial velocity or final velocity. So I'll take the average velocity. So to calculate here, what I'll do, I will take this d as average between both, because we don't know, right? Because it is continuous operation, right? So I will take the intermediate diameter. Okay, I cannot take 20 because you feel that the cutting velocity is 20. The cutting velocity, if you take as 20, it will have some velocity. If you have take 19, the cutting velocity will come down. But the operation is happening throughout. So I'll take d average is equal to d initial plus d final by 2. That would be a best option to take. So this will be 20 plus 19 by 2. So this will be some 19.5. Let me substitute here as d average. Okay, Vc is equal to I into 19.5 into what is the RPM here? 600. 600. Okay. So now what I'll do? I'll substitute all the values. Finished. So if you see here, MRR, FD, VC. Right. So F is 1 by 3. Depth of cut 1 by 3, sorry, is 1 by 2 or zero point 0.5 into pi into 19.5 to 600. If you calculate, you'll get an approximate value, but I have the exact value. The exact value is 612 some mm³ per minute. But let's check the options. Okay, so it is nearly equal to this A. Okay, so no need to calculate complete value, exact value. So once you calculate the 6, that is enough. So nearly is 6100 per minute. This is the answer. Again, I have done it very elaboratively. You can do it in, like, the calculations are more, so you can do it within 2 minutes. If you are very good in calculations, you can do within 1 minute. Okay, good. Let's proceed. In a casting, this is from casting. In a casting process, the horizontal channel through which molten metal flows from pouring basin to reach the mold cavity. Simple. Simple question. Seconds. In seconds, you can answer. So this is your this thing, right? This is your mold cavity. Okay. This is your mold cavity. And what is this? This is your pouring. Okay, let me take different ink. Right. This is your pouring basin. Pouring cup, you can say. What is this? Screw, down screw, right? And this is what is your runner. and this is what is your in gate, and this is your cavity. So what is the question? A horizontal channel. So this is horizontal channel from which molten metal flows from pouring basin to reach the molten unit. This is the answer. Runner is the answer, right? So you see thinner corridor riser. Spelling also is riser is nothing but when you have something like this. This is what is your riser. It will compensate the shrinkage. So answer is runner. Simple. Okay. Proceed. Next. This is with the additive manufacturing. That is 3D printing techniques are. So they're asking which one of the following is 3D printing, and they're asking the option as all are 3D printing techniques. So according to me, all are 3D printing techniques. So what is this? The answer is all, but I'll explain what is what. Selective laser sintering is nothing but you have some kind of powder materials that are placed onto the bed, and then you specifically put it on laser on certain path, and where you put the laser there the powder materials will be powder particles will be melted and fused together, and thus bonding is occurred. So through that you can try to build layer by layer and get to the final part. That is one of the method. Selective laser melting also is another method where you have some kind of fully sorry, selective laser sintering is that melting is you have some powder, and then you typically melt it and flow it. That is what you do it. Okay. So the powder is fully melted rather than sintering. Here sintering is nothing but you are putting the material and applying heat onto the powder particles so that powder particles are joining together with a small amount of heat. But here melting means you're melting completely powder into the liquid. That is what is your selective laser melting. This is another method we can use. Electron beam also can be used for heating the powder materials. So all these things can be used for making a 3D printed part. So that's why answer is all of the above. Okay, good. Now, next is what is the kind of deformation that occurs in shape memory alloys? So what is shape memory alloy? Shape memory alloy will get back to its original position applying under some deformation. After some time, if you apply some heat, it will come back to its original position. So that is what is your meaning of shape memory alloy. It will remember its shape. You will apply, it will deform, and you apply some heat to it, it will come back to its original position. So that is what is your shape memory alloy. So which one of the following is kind of having a deformation in shape memory alloy? So so what kind of a deformation that is occurring in shape memory alloy? Right? Is it thermoplastic, plastic, thermoelastic, or none? Okay. So we'll go option by option. Thermoplastic. So this thermoplastic is a permanent deformation because plastic means permanent. So even though this shape memory, whatever it is, it will not come back because of its permanent deformation. So this deformation will not reflect the shape memory alloys, right? So when some plastic material is heated, no, it will have some external forces, let's say, or maybe you apply some external. So the reversible action will not happen because shape memory will have some reversible action, right? And plastics are having some kind of deformations which are again permanent in nature, like so again plastic permanent. So thermoplastic or plastic, forget, both are permanent. Thermo means under thermal, plastic means plastic deformation. Thermoelastic, right? This can be reflecting the deformation in shape memory alloys. Okay, where material can undergo some deformation, right? But at one temperature, you can get back to its original shape, right? So that's called transformation temperature. The temperature which it can come back to its original position is called transformation temperature, right? So answer is C. Example, for example, the example for this material of shape member alloy. we can take as we can call it as nickel titanium alloy. It's called nitinol, but yeah, I'll write nickel titanium alloy. So this is one of the example for sheet memory alloy. Okay, good. Next. It's a very good question again. So the phase milling, again the question is coming from the milling operation. Phase milling operation is carried out with, let's write what is given. Let's write what is given. Given diameter of cutter is 100 mm, milling cutter. Cutter teeth Z as 4, right? Number of teeth, right? And spindle speed RPM is 300 RPM. N is equal to 300. If feet per tooth, so feet per tooth, I'll denote it as FT, that is 0.125 mm. Okay. And what is table feed in mm per minute? Here we have to understand the difference between feed per tooth and table feed. Okay. So what is that? So you have this cutter like this, right? You have this cutter. So something the cutter is not looking good, but think it of as a cutter, milling cutter. Okay. So this is one tooth, another tooth. So how much feed you are having? So this is the table. Okay. So please remember the cutter will rotate and feed is given to the table. Right. So how much feed, how much table is moving, how much table is moving for one tooth in action is feed per tooth. And table feed is in generic feet per mm per minute. Okay, so feet per tooth will be given by per tooth. So FT, the units will be per tooth. And table feed, table F table will be per minute. Okay, so there's a difference. So they're asking what is the table feed. Okay, so table feed, generally table feed F table or FM, people write it FM, but I am writing it F table, will be per revolution into number of revolutions. So this is feed in per revolution. Okay, this per feed in per revolution can be given as feed per tooth into Z, number of teeth. So substituting this and this, what will I get? Feed by table will be FT into Z into N. We have discussed in our class clearly about all these things, right? Same thing. So F table is what they're asking. F table is feet per tooth. How much is that? 0.125 into Z. How much is a tooth? 4. Number of tooth 4. Teeth 4, sorry. And RPM 300. RPM 300. If you calculate the feed table, you will get the answer as 150 per. Let's see what is the option. Option number is C. Simple question. Simple question. So we have to know the differences between table feed, feed in per revolution. This is per revolution. Right. This is in per minute. This is in per tooth. So units are very, very important. With units also you can try to find out the answer. Okay, very good. Let's proceed. Now, which is the correct sequence of machining operation to be performed to finish a through hole of large diameter. So you have some kind of a material, you have to make a large diameter hole, which is a sequence they're asking. Simple question. First, what you'll do? Nothing is there. Simply you can't do boring. Now, what is boring? Boring means enlarging hole. Reaming is for surface finish operation. Without making hole, how do you make the big hole? How do you make the surface finish? So first you have to do the drilling. So drilling. So these two options are gone. After drilling, you will not do surface operation, right? You will do the enlargement of holes. So then boring, then surface finish operation, ringing. So hence, answer is very simple question. Very simple question, right? So drilling is the first step, followed by the enlargement of size, and then finishing of the hole, right? Reaming for finishing. Finishing. And boring is enlarging hole. Good. Okay. Now, these are all simple questions. In abrasive jet machining, the main mechanism of material removal takes place due to, in abrasive jet machining, what we'll do, we have some compressed air. That compressed air is coming through some, different route where we have some heater to eliminate some, moisture in it, and then we'll come pass that air to a compressor. It'll compress, then it will go to some place where there is a chamber. In that chamber, we'll add some abrasive particles, and these abrasive particles with compressed air will be going into a pipe, and then it will be coming out through a nozzle, and that abrasive particles will hit the workpiece, and thereby some brittle fracture will happen and material removal rate will happen. So here you do not see any electrical or electrochemical action. You do not see any ionic dissolution. You cannot see any melting and evaporation. Only mechanical impact. Answer is C, right? So what is electrochemical? These two, no, these two will be coming for electrochemical machining, right? Electrochemical machining, it's called ECM, right? ECM. What you do? You have NaCl plus water is a electrolyte. You put your workpiece, right, and tool inside, and maintain a gap between tool and workpiece, and then you start the electricity. Because of that, some chemical reaction will be happening. Through that series of reactions, your material will be removed at atomic level, atomic dissolution, they say, right? And what is this? This will be for electric discharge machining, EDM, right? So answer is C here. Only mechanical impact, nothing else. Simple. And what is the use of this? Because see here in A, B, and D, you need to have electricity. In the sense, your material and tool should conduct the electricity. But here in abrasive jet machining, no need of any material that will have to conduct the electricity, right? Let's like ceramics and all. So for machining some kind of materials like ceramics and all these things, you'll use this. Okay, very good. Next, 70. So the preferred choice of steel material for a cryogenic explosion. So here the thumb rule is cryogenic. Cryogenic means low temperatures, very low temperatures. Okay. Now they're asking the preferred choice of steel material. So please remember, if you have a structure which is FCC in nature, right? If you have some structure which is FCC in nature, what happens? They have good ductility and they have good toughness. Okay. So then what will happen when you have when you reach to the low temperatures, then what happens? These materials will still remain in ductile nature. These FCC structures will be still remaining in ductile nature. If you reduce in temperature, generally the ductility will go to brittleness, right? So that is called the ductile to brittle transition, right? So please remember, FCCs are good at low temperatures. Means ductility is maintained. So here there are ferrite, austenite, and martensite. So here I would say Farad is in BCC, so this is not good, right? Okay, BCC will not have, will not maintain its ductility under low temperatures. It will come brittle and then it will have brittleness. So brittleness is not good, right? So obviously it is not preferred choice. Austenitic is FCC, so this is preferred. And Martensite is very hard, right? It is one of the hardest form, very hard form. Hard means I can assume that fine grain structure, something like that. So under low temperatures, there may be a chance of brittleness. So that brittleness will not be a good choice for your cryogenic application. So I feel, not I feel, the answer here is austenite because of its FCC nature, the phase centered cubic nature. That's why austenite is very important in I mean, this kind of can be a preferred choice for my cryogenic applications. Okay, are ductile, not good, ductile. Sorry. Okay. Next, which of the following is not a casting defect? Which of the following is not a casting defect? Okay, blowholes is casting defect. Blowholes is casting defect. Cold shut is casting defect. Hot tear also is casting defect. This is not casting defect. What is this? This is a welding defect. Spatter, right? Because this is what casting defects. So which of the following is not? So spatter. Okay. What is spatter? Because of arc blow and all, the material, there is some pitted area around the weld bead, that's called spatter. Right? If you have arc blow, the spatter will come. Blowholes is because of some porosity. Cold shut is because of insufficiency of fluidity. Hot air is because of the thermal gradients. Right? Because of all these things, these last three are casting defects. Spatter is welding defect. Okay, very nice. Next. Next. So, which of the following improves weld ability of steel? Low carbon, high carbon, and poor affinity to oxygen, good affinity to oxygen. So please remember, if you have high carbon, right, then what happens? The high carbon will not be good for weldability because again high carbon, again you are heating it, right, leading to formation of some hard and brittle structures, some kind of carbon. Carbon is very brittle in nature, hard in nature, right? So if you're heating and cooling, there is a problem, right? So please remember the thumb rule also like this: low carbon steels are good for welding, high carbon steels are not weldable easily. We have to do it, but those are not weldable. So low carbon steels are weldable, high carbon steels are not weldable. So the here I would say that low carbon is one of the option. Low carbon, and they're asking whether the area, it should be having good affinity towards oxygen or less poor affinity towards oxygen. If it is having good affinity towards oxygen, the material, then again the oxygen will go attack the weld pool and the oxidation is formed. Because of the oxidation, what happens? Your weld metal will become dirty and also it will form to the brittleness, or maybe it will have some kind of defects. So hence you have to have poor affinity, right? So low carbon, poor affinity to oxygen. So answer is A. Answer is A. Okay, good. Yes, Tejeshwar, you're right. Answer is A. And next question, and that is last question for our manufacturing part. Next we'll discuss the industrial part. The commonly used flux for brazing is borax. We were keeping on saying borax, 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 right? What is the use of this flux? It will remove the impurities. It will increase the surface tension or wetting action. Epoxy, as generally epoxy are used for, yes, you're right. Epoxy is used for what? The epoxy is used for adhesive bonding, not the brazing bonding. Inert gas is used in welding. Inert gas is used in welding to avoid the contamination of weld pool from the atmosphere. Okay, so that is it for our, yes, that is it for our manufacturing part. So now let's discuss the industrial part. Okay, let's discuss the industrial part. So what is this? A manufacturer has the following data regarding the product. What is that? All are given. So here fixed cost FC, fixed cost FC is given. Variable cost VC is given. Selling price SP is given. Production capacity, production capacities. Let's not write PC. Let's not have. So those are all prices. I have written prices, but let's not write small symbol for PC as production capacity. Let it be like that. Now what they're asking, if the production is carried out at 75% of, oh, you didn't get it. Oh, okay. Maybe some calculation mistake. We'll see. Answer is 1 lakh. You're right. The production is carried out at 75% of rated capacity, then the monthly profit is. It's a very simple question. Okay. Generally, what we'll do, there is an equation. What is that? Your fixed cost plus your, the variable cost. This is variable cost per unit, right? But how many units you're producing? 16. Let's forget variable cost. Variable cost plus profit, right? Plus profit is equal to your selling price SP. If your profit is not there, only these two are there, then that is break even. If profit is not considered, let's say, then that is break even. If you have profit also considered, then you have crossed your break even, right? So we'll write this. This is the equation, simple equation. What is fixed cost? What they are given? 80,000 rupees they have given. Very good. So 80,000 fixed cost. Variable cost 350 rupees into 16 units per month, right? 350 into 16. Okay, here one more important thing here is the production is carried out at 75% of rated capacity. It means that 70 production, the units produced, the production capacity is 75%. So it is full percent here. They are saying that this is full, but the rated capacity 75% only is produced. That is 75% of 1600, right? So monthly production is equal to 0.75 into 1600. That is 3 by 4. 3 by 4 is 400, 4 3 is 12. So this will be 1200. That's it. Now 1200 should be used. So this will be 1200. Plus profit is equal to selling price. What is selling price per unit? 500 rupees you are selling, right? So 500 rupees into 1200. Now you have to find the profit. You can just calculate the value. You'll get the value of 1 lakh. Simple. That's it. right? Answer is 1 lakh. Next. This is simple again, very simple, only matter of minutes, seconds you can do it. For PERT activity, the optimistic time is 6 minutes. The most likely time is 9 minutes. Pessimistic time is 16 minutes. What is optimistic time? You are too optimistic, there is nothing. You are too optimistic, there is no delay, nothing is there. So you can complete the activity in 6 minutes. Everything is in flow. Most likely is generally what is up. Pessimistic means every where you are getting stopped and you are assuming that there is some issue there, and then you are very pessimistic, very negative thinking, right? So that is what is the maximum time. So if you have these three estimates, then what you have to do, you have to find out the expected time for the activity. This expected time of activity will follow beta distribution, if you remember, right? So if t naught optimistic time, sometimes they'll write it as a also, I'm writing 6, and tm they're giving us 9. Let me write minutes, and most likely time is 9 minutes, and pessimistic time TP is 16 minutes, right? So expected time is nothing but TO plus 4TM plus TP by 6, right? So this will be 6 plus 4 into 9 plus 16 by 6. So this will be 6 plus that 39 is 36 plus 36 is 42. 42 plus 16 is 58. 58 by 6, right? 58 by 6. Oh, they're asking in seconds. Okay, into 60. This is 10, so it is 580 seconds. That is again very simple question, right? Next, let's go for the last question for our industrial part as well. So for a project, 6 activities are to be carried out. The precedence relation and duration of activities are as per the table, and minimum simple. Let's draw the activity. First you have to draw the precedence diagram. So let's start with A, right? Let's start with A. So you don't have any predecessor. So A, and then B for A. So B will come out, right? And then C also for A. Okay, A. And then B for D. So this is D. C for E. Okay. And F is D. Okay, these two should come F. So I'll join these two. D and E I'll join, I'll get E, F out of it. R is very important, don't forget. So D, E, F. Right? Let me write this as 1, 2, 3, 4, 5, 6. Now what is the time? Duration time 6. So let me write here with different ink. This is 6 and B is 5. A is 5. C is 8. D is 8. D is 11. D is 11. E is 6. And F is 7. Now we have only two paths. Simple, very simple. Two paths only there. Right? So let's take path 1. What is the path 1? Path 1 is 1, 2, 3, 5, 6. Calculate the time here. Calculate the time. The time here, what is the time? Project completion time. Let's write project completion time. PCT, project completion time is equal to 6 plus 5 plus 11 plus 7. Right? 11 plus 22 plus 7, 29. 29. Is it days here? Days, yes. And path 2, 1, 2, 4, 5, 6. Again, project completion time, PCT time is equal to 6 plus 8 plus 6 plus 7. How much is this? 12 plus 8, 27. Right? So the maximum you have to select. Right? This is the answer. If you have a very complicated diagram, you have to go for the forward pass and the backward pass, and then identify the forward pass nodes and backward pass nodes and see wherever there is zero float and identify the path, and that path will be your critical path. So this is your critical path here. Area maximum. So this is the answer. Answer is what? 29. Very simple. Right. So that's it, guys. So that's the solution for the manufacturing and industrial part. If you have any other doubts, please do contact us, or you can even comment here. We'll be able to answer your queries. Thank you.